Get this. I've got so much trouble in my life. Okay, it's not working. Awesome. Yeah, I don't know. Yeah, maybe the red light just means it's low on battery. There's a separate battery thing that. Anyway, hopefully it's working. Yes. So the question I was asked has to do with this cross-contamination. So in the paper, we look not just at the density, local density of treatment schools, but we also look at the local density of all schools. And what's very interesting about what comes through in the paper is exactly your point, which is if you're located near more schools with more of this potential for cross-contamination, there's more kids nearby who tend to be very infected, et cetera, this population, this tends to be positively associated with infection. Whereas having more treatment schools nearby tends to be negatively associated with infection. So the intuition you had comes through in the data that if you happen to be located near lots of schools in general, there's more disease. And people have commented for a long time that, say, when urbanization has occurred, along the way, sometimes people's likelihood of getting infectious diseases actually increases. So you might think, oh, I can go from a rural area to a city. Cities are richer, people will be healthier. No, if people are really living in very dense conditions in close proximity, that may actually increase the spread of infectious diseases like worms or typhoid or cholera or these other things. So let's go through the estimation. Now, what's different about what I'm going to present here is you're going to recognize this equation. It looks a lot like what I had before. I even have the same C term. It's also an externality term. But now, that's going to be the cross-school externality term. So how am I thinking of it here? We're going to think of that P, T term as being the proportion of local students, say within 6 kilometers, that are in treatment schools. Now, in the paper, we don't do it that way. We look at the number of treatment schools and the total number of schools and look at both of those separately. And we do that for two reasons. One, to look at the effect you pointed out, which is total local density can have an effect on its own. B, when we do cost-benefit calculations, we actually want things in terms of like number of kids treated or number of kids exposed. It makes things easier. So we do things in numbers. This PT term that I'm focusing on the estimation here is basically just this NT divided by M. And it's just going to kind of put us in the same framework, but for people reading the original paper, we break these terms out, and then we have an appendix table where we look at proportions just to show the effects are very similar to looking at proportions. So let's walk through this. Again, we're regressing some educational outcome on assignment to treatment, but now we have this exposure term to other treatment schools, PT. And that term is going to be close to 1 if I was in that blue circle. Almost all the schools around me are group 1 schools. So everybody kind of around me who might be infecting me was treated. And that term PT is going to be close to 0 if I was in that red circle, where like no one was getting treated. So my reinfection rates are going to be the same as they were before. I'm not benefiting from this spillovers of the program. And the term C is going to tell me how sensitive my own infection is to this reduction in reinfection from having other people near me get treated. So it's very much like the externality term we had before. That's why I kind of kept this common framework. Let me pause if there's any questions or thoughts about this specification. I think you guys are familiar with it by now. You can do it either way, and you get similar results. So we've run it either way, and actually, to be honest, we're forgetting how we did it in the 2004 paper. I had to remember, because I know we did it one way and the other. Maybe the referees for the journal asked us to do it both ways. But it doesn't really make much of a difference. If there were really large differences in the take-up rate of the drugs across schools, it might. But as long as the take-up rates are pretty comparable, then it's not going to make too much of a difference. Yeah.
When there's no interaction term, it seems like it's not just because of the you have relationship between it seems like there'd be interaction, not just but also your density too.
So you want the interaction to be between the treatment dummy and NT and the treatment dummy and N?
Well, I'm thinking PT interacted with like density of
Mm-hmm.
kids, because it's very different in the sense of kids are treated with like 2 kids in the area as opposed to
Yeah. Again, we went back and forth and we kind of showed things different ways. The interaction between PT and the total density, PT times N, is just NT. So in some ways, focusing on that kind of raw number gets us back to the specification in the paper. You could include PT and also M. So you could, the problem we faced here to some extent is when we were working on this estimation, we felt like there was too little guidance from the epidemiological literature on exactly what the functional form should be. And we talked to epidemiologists and even read some of the textbooks of like, okay, how exactly does this transmission happen and what would the right functional form be? Should it be interaction? Should it be linear? In general, epidemiological models at some point of treatment, they're very sharp nonlinearities. When you get to the point where like almost everybody's treated, then you could even have a disease go extinct or something. So it'd be very sharp nonlinearities. We didn't think we were at that point here. So we start with this very simple linear additive specification. And one thing that we did do, and we do talk about in the paper, the 2004 papers, we do at times run interactions of the treatment dummy with the number of local treated, but we typically don't find very strong interaction effects here. I thought that was the interaction you were talking about this other one. So you might think that you can imagine a story where if I receive treatment, maybe my reinfection patterns are different. I'm treated, the worms are all killed off. Maybe I'm better able to fight off the worms or something. So maybe reinfection rates are particularly slow if I was treated already. That would be sort of one sign. The sign that interaction could go the other way too, which is maybe if I'm so full of worms, I'm like really heavily infected, maybe I'm less susceptible to further worm infections. There's like less space or something. So we didn't know. Like we would come up with these stories and talk to people, but we didn't get enough guidance from empirical work in epidemiology. So we've sort of started with the simple linear specification. What are other people's thoughts? We're very sympathetic to these points. We just haven't been able to make much progress. What are other regression specifications or ways of thinking about the reinfection environment that come to you when you think about this setting that would change the way we do these estimates? I mean, the other thing we run into is limited statistical power. And whenever you start including multiple interactions, we have 75 schools, and we're looking at subsets of the 75 schools, so the sample sizes start getting small too. So part of the reason why we fail to find these interactions might not only be because there's no effect for these interactions, but just because our standard errors start getting really big and we start looking at subgroups. So that's the other thing we face. Yeah. In terms of the kinds of externality effects that they experience, we do have specifications that have the within school terms and the cross school terms in the paper. I'm trying to remember what the results look like if you do interact the D term we had before with like this PT, and they're not in the paper, I don't think, and I'm just not sure what they look like. I don't remember. Here for you guys, I'm just sort of illustrating within the cross school, within school and cross school. In the paper, we have specifications with both the within school terms and the cross school terms. So there is a kind of like integrated estimation, trying to get all the externalities at once, and that's what we base a lot of our conclusions off of. Yeah.
Was there any infection of infection by using the student data, not the school data?
To get infection using the student data.
Yeah, because I'm not sure that school district or something, but the kilometer boundary might just
Yeah.
might be different.
Yeah, so that's a great point. In the data set, the way we collected it, we have geocoding. We have the GPS locations of the schools, but not the kids' households. In basically later surveys that we did after 2000 or 2001, another project, we would always geocode all the households. But at this time in the late 90s, like the project had like a couple of GPS machines, and we basically, it wasn't like now. It's harder to do. So we had school GPS locations. For a subset of these households, but only for a subset of the group 2 and 3 households, we do have some household geocoding for a subsequent activity. I have to think if we have enough data to try to link it back here, because what you're pointing out is very interesting, because the individual exposure to treatment schools really comes through not just where you go to school, but where you live. So some of these guys, if we go back to the map, if I'm in that blue circle, but I happen to live in the bottom right-hand corner, and I walk to my group 2 school, I'm kind of close to some of those group 2 and 3 schools down there. I may be less exposed than someone that literally lives right in between those two group 1 schools, right? So that's the kind of variation our data won't let us exploit, but that's like the right way to do it. If we had the data, that would totally be the way we'd want to construct the externality exposure. So that's a great idea. Yeah?
Why do you use it
What ends up happening with this data is that the farther out you go, the more schools you have in one of these circles, of course. And the more overlap there is in the circles of the different schools, as the circles start getting really big. When there's more and more overlap in those circles, the amount of effective variation you're getting in exposure to treatment schools actually goes down, because all the circles are starting to be really big and sort of containing the same schools. Imagine a circle that has 100 kilometers where they have all 75 schools. We have no variation. So as you get bigger and bigger, you have less and less variation in this PT, and the standard errors start going up more and more. So we chose 6 kilometers really just because when you go from 4 to 5 to 6, the standard errors start getting bigger and bigger. And at 6 kilometers, we still had some reasonable precision in terms of our estimates. And then after that, the standard errors get so big that it's hard to say anything meaningful. The basic thing, the intuition when you're looking at regression results or you're thinking about analysis, I think it's a good lesson, is if you have an explanatory variable, the more variation you have in it, in that explanatory variable, in general, the more precise your standard errors are going to be. It kind of makes sense. Like, you just have a lot of cases to work with. It's the opposite intuition for your outcome variable. If you have an outcome variable with tons of variation, then lots of that may just end up being noise, and basically your standard errors become very large. So when we increase the circles to be bigger and bigger, and we have less and less variation in PT, our standard errors just get really big, and we don't have very much precision in our estimates. Yeah?
You were saying you were sure if they meant to make the rate or not.
Yeah.
Did you use schools with a high uptake rate versus schools with a lower uptake rate for the plot, like how for A, surrounded by other people that are different enough?
We have done. I know when we take into account school take-up measures, we don't find big differences. I mean, you're right that what we really want is as much variation as possible in local exposure. One of the things we did, I think we mentioned in the paper, we've definitely run it, is we have looked for like quadratic terms. So far here, if you go to the regression estimates, the key explanatory variable is this PT term. But you could easily also look at PT squared, say, and see if you see some sort of quadratic relationship. We have very large standard errors on PT squared. We have very little precision here, and the point estimates tend not to be statistically significant. So we sort of gave up in taking advantage of that variation. But those are the kinds of things we were doing with the data. Exactly what you're saying. Okay, so I think you guys are familiar with this. We're going to focus on this proportion of treatment school pupils. And what I want to do now in the next just couple slides is walk you through how we quantify benefits of the program, taking into account these externalities, because this is what delivers a lot of the cost-benefit numbers in the paper. So, this goes back to the kind of clicker question. What treatment effect would we estimate if we want to understand a real-world program? In this context, and leaving aside the within-school externalities, what we really want to do, the experiment we want to have in our mind, is a case where I'm treated and everybody around me is treated. So PT equals 1. Like everybody in the relevant local area is treated. And I want to compare that person to an untreated person in an area where PT equals 0. Where like in the relevant area for local spillovers, no one is treated. That's the closest thing to like the pure treatment effect of mass treatment in some areas, pure control in others that we can get to. So we want to compare T equals 1 and PT equals 1 to T equals 0 and PT equals 0. So let's write that down given the estimation equations and kind of use similar notation to before. So we want to compare the expected outcome in terms of the educational outcome Y in those two cases, T equals 1, P equals 1 versus T equals 0, P equals 0. As we said, there are some isolated schools where PT is 0 in our data, so we do have some people at that extreme. We have other schools where PT doesn't quite get to 1, but it gets pretty high, like the circles I showed you. So we have a considerable amount of variation here. So if we go through this difference, we get here. Now, the key step here is, because of the experimental design, we make the case that expectation of X, these unobservables, the socioeconomic characteristics, all these other things, should be similar if I'm a treatment school, T equals 1 or T equals 0. We already made that case before. And whether the schools near me are treatment or control, because they were also assigned through the experiment. And again, when we check the observables of schools that are T equals 1, PT close to 1, and T equals 0, PT close to 0, they look very similar. So in the data, it looks like the experiment did create comparable, not just direct treatment assignment groups, but also exposure, similar groups in terms of exposure to externalities. And there we get B plus C. So that's what you would have guessed all along. The overall treatment effect is the effect of being assigned to treatment plus the effect of everybody else around me getting treated. And again, the big caveat here, people have been pointing this out in different ways, is we might expect the treatment effect maybe to different treatment schools, there could be nonlinearities, there could be interactions. Maybe the treatment effect isn't simply additive, B plus C. But we can't reject in our data that it is linear. So we go with this specification. And of course, B plus C is greater than B. So before, when we were doing the simple difference between the treated and the untreated schools, we were getting B. But just like when we looked at treated and untreated within the treatment schools, we're kind of underestimating the effect. All the estimates I showed you before in terms of health effects are understating the true effects because they're missing the cross-school externality, which means the treated are gaining more if they're surrounded by treated, but even the untreated are gaining if they're surrounded by treated schools. So this is basically the same algebra as within school externality effect. So let's actually just work through what the gains would look like. We have this estimation equation. Let's allow the actual value, the average value of PT to just be called little p. The average of this local exposure to externalities is p in our data. Because of course, we don't literally observe treatment rates of 1 versus 0. There's some, in reality, if we want to get the benefits to this particular program, we want to know that number, the average exposure to externalities in this sample, in this context. So now we're comparing people who were treated with this sort of average exposure to externalities versus the untreated with 0 exposure. That's the benefit to the treated, that first row. And why is that multiplied by p? which I told you is the average of this kind of exposure. Yeah. If the fraction of people in the area who get treated is p, little p, then that's the group that is treated. That's the fraction who are treated, where t equals 1, say. But it's also going to have to end up being this number. If we average the PTs across schools, it's going to have to average up to the overall treatment rate, which is just total number treated divided by the total population. So it turns out that little p appears in both places. It's going to affect what the average spillover exposure is, but it's also the fraction of people benefiting from treatment. 1 minus p are the people not getting treatment. So you see for the 1 minus p people, t equals 0. And we want to understand the average impact for the people who are untreated. So again, average exposure to externalities is pt equals p minus pt equals 0. So there's like an algebra step that I didn't put in, but the basic point is if a fraction p of the area are treated, that's going to be the fraction for which t equals 1, say, here, roughly, but close to, with good compliance. And it's going to tell us something about exposure to externalities. So if you go through the algebra, what do you get? This is proportion treated and average gain among the treated. Proportion untreated times average gain among the untreated. The gain among the treated is this b effect, the direct effect of treatment, times c times p. P is the, p doesn't equal 1 here. It's something between 0 and 1. The average effect among the untreated, fraction 1 minus p, is just the externality effect. So the algebra just works out to the following. Yeah? Yeah. 400 kids in these primary schools. And they're pretty close together. And there's a lot of reasons why there are these cross-school externalities. One is people don't always attend the school closest to them. They will sort of walk a few kilometers to school if the parents like the headmaster or if an older sibling is already at that school, etc. So there are people who attend different schools who are neighbors. And there is that kind of intermixing. You saw how close the schools were. So that's part of it. Another reason why you find these spillovers is, if you go back to the map, people live, sorry, I'm jumping so far back, but a lot of these schools are near Lake Victoria. And kids very often go to play or fish or bathe at the same points on the lake. And that may be true for kids from a few kilometers around. So kids from a few kilometers around may attend different schools, have different treatment status, but they may all be accessing the lake at similar points. So some of those kids are, the way the schistosomiasis mannsonite is sort of this type of schisto in this area spreads through fecal matter. If kids are defecating in the lake on those points, they're basically infecting the other kids who didn't play exactly that part of the lake. The snails also swim, so the snails can move slowly because they're snails, but snails can move. So there's a bunch of reasons why you get this kind of geographic spread of the externalities. Yeah. The schooling rate in terms of school attendance? We'll talk about it just next. The next thing I'll get to is exactly school participation and these kinds of things. Okay, so let me go forward. We've gone through this. I know I've gone through this a little fast, but I'm doing it in parts because I want to get to more stuff. This is just algebra. If you understood the within school externality, the cross school externality is the same estimation equation. It's just a different way of thinking about it, and the overall effect is still b plus c. Yeah. Yeah. Yeah.
But obviously, I think there's an option for a PT integration anyway. So they're asking people to disregard it. The coefficient is not really here, right?
B could change once you condition, potentially, the estimate of B could change once you control for PT. And that's like something you also find in the data too. So that's also correct. That is also correct. If there isn't perfect independence between T and PT, then including PT could affect the estimate of T for sure. And that could lead you to further understanding. That's something I haven't gone into, but that's right. That's correct. So there's a bunch of reasons why previous studies are understating the benefits. Okay, educational impacts. I want to get to education and exactly the point you're raising, but now's the time for the next clicker question, which is just sort of before we get into all the different dimensions of education, for people who've read through the paper, you kind of have some sense of what de-Werning did, but independent of what de-Werning did, I'm just interested in people's views. If you think about the types of schooling measures that you think would correlate with later labor market success, earning a lot of wages, earning successful occupation, which of these dimensions do you think is probably going to be most important? Is it going to be school attendance, just sort of showing up, taking part in school? Is it going to be your test score? Is it going to be the kind of extracurriculars you do? Being good at art or sports or all these other things? Or maybe all the above. Maybe they're all kind of equally important. I'm just curious about people's sort of prior sense about some of this stuff. Yeah. Yeah. I'll let you choose the interpretation you want, because I don't have a good answer. It could be, maybe because this is elementary school, maybe just think of like being enrolled and attending elementary school for some period. I'm not sure how long time frame I want to think of. Yep. Okay, so let me just stop the poll. And okay, it's pretty interesting. So people think attending matters. There's a school of thought that is very much in line with that. Jim Heckman, who's a Nobel Prize winning economist at UChicago, has had a series of papers over the last decade talking about all of these so-called non-cognitive traits that affect labor market success. And if going to school means you learn to show up on time and be reliable and be punctual and be polite and answer questions and be nice to your neighbors at your desk and do all those kinds of things,